Principal mathematics / principal physics. Particularly for this presentation, we have a simple topic that is found in both disciplines, that is mathematics and physics. This is a tutorial for basically students in senior 5 and senior 6 taking principal physics and principal math as the subjects in their respective combinations. So without wasting any microsecond, allow us hijack this very small topic, motion under gravity, and in particular projectile motion. So we shall start with a definition of a projectile, which is none other than a situation where a body is thrown within a given velocity, which is actually the initial velocity, and allowed to move under the influence or the action of gravity. For example, when a ball is set into motion, and for this very particular case, we can highlight an example of a ball hit by a cricket bat. You can talk of a shot put thrown by an athlete. You can talk of a bomb thrown from an aeroplane. Talk of a ball taken as a free kick from a certain sport. All those are some of the examples that can give us an image of projectile. However, projectile motion can be in three phases. Phase one, we can take a situation where a body is vertically projected, probably from a certain height, and is projected vertically. So that is vertical projection. We can talk of a body being projected at an angle, and then the body is allowed to describe a parabolic path or a parabolic path. So for that case also, from the horizontal ground, we can still resolve the components of the initial velocity given to that particle. We can also talk of a situation where a particle is projected from a certain height, from a certain cliff of a given height, and it's launched horizontally, and then it's allowed to hit the ground. So in this very particular presentation, we shall look at a case where the body is projected at an angle with a horizontal, and basically it's from the ground level. So for that case, we shall look at motion of a particle, and we shall study its vertical component and also horizontal component, basically the initial velocity. And if that is the case, if the body is just projected with the velocity u at an angle theta to the horizontal, then the horizontal component of that velocity will remain constant throughout the trajectory. And on the other hand, the vertical component will keep changing from one point to another. Initially, it will be u sine theta. At maximum height, ceases, becomes 0. Then at a certain point, just after the maximum height, it will scale down to a certain value that we can just calculate using the equations of motion. Examine this case where a particle is projected from a certain point, and then it performs a parabolic path and hits the ground after some time. Meaning, from the point of projection to where it hits the ground, it covers a certain distance r. We shall call it range, as the distance covered by the particle from the point of projection to the point where it hits the ground, and that's distance measured horizontally. However, it's possible to have that distance also called maximum, and that's when the particle is projected at an angle 45. So we need to look at this particle basically starting with the initial velocity. Since it is projected at an angle, we shall have to resolve the initial velocity. We agreed velocity is a vector quantity, so it is defined by direction. So we need to look at the direction components of this horizontally and vertically. So, and another thing, we need also to look at a case where now the body is attaining a maximum height, and at that point, the initial velocity, the final velocity at maximum height will be equal to 0, because the body is taken to be at rest momentarily. It takes some small time in space before it gets to the ground. So at that point where it attains the highest point, attains the highest height, that point is determined from the ground as the maximum height. So for that case, we agree the velocity will be equal to 0. So that very height, vertical height, is maximum height. Then we agreed that from the point of projection to where it hits the ground horizontally, that's the range. We shall also look at just after the maximum height, if this particle is actually describing a parabolic path, it means we can also study the particular particle at a certain point, meaning the horizontal component and the vertical component at a certain point just after the maximum height. And that will help us to get the velocity with which this body, if it is a ball, projected to clear the wall, projected to clear a post, projected to clear a bar, that's the velocity with which that particle will clear the wall, given the height of that wall intended. So we shall also find the angle at which that final velocity with which the body clears the wall makes with the horizontal, and that angle will be called alpha at that point. For this particular case, we agreed initial velocity has to be resolved horizontally, which is u cos theta, and vertically u sin theta. And it is also possible now that we are studying this particle at a certain point just after the maximum height, meaning there is a height from the ground vertically to that point, and also there is a horizontal distance from the point of projection to where we are studying that. So the horizontal distance will be x, and then the vertical distance will be y. So within this structure, we need to extract very many equations that will help us to calculate the missing perimeters in the context of projectile. So considering the vertical component of motion, we realize that initial velocity vertically will be u sin theta, and acceleration will be a negative g, which is negative g meters per second squared. Why is it a negative? It's because it is acting against the gravitational pull. So when we let h be the maximum height, h capital, then it means at maximum height, of course, the velocity component, the velocity component vertically will be equal to 0. We agreed on that. The body appears to be at rest momentarily. Using the equation v squared is equal to u squared plus 2as, substituting in the perimeters v as 0, initial velocity, vertical component u sin theta, of course it's squared, and then g is a negative, h is a maximum height. I will get my maximum height in the red color given as u squared sin squared theta over 2g. And that is the expression that we shall be using to find the maximum height attained by the body on a condition that 1, you have the angle of projection, 2, initial velocity. If you have them, substitute in the formula, get the answer to the required decimal places, to the required significant figures. Look at this, the vertical velocity of the particle at any point on the trajectory. And for this particular case, I'm looking at a case where now it is after the maximum height. So we shall use still the equation s is equal to ut plus half at squared. And for that case, since the body is not against the gravitational pull, the acceleration due to gravity will be a positive meters per second squared. When I substitute in here, if I have y as my vertical distance measured from the horizontal ground to the point where I'm studying that particle, and I have my t as time at that point, which I can also get from measuring the horizontal distance from the point of projection to where I'm studying that particle, and also the initial velocity horizontal component, which is u cos theta and x. So when I substitute in back, I get my answer, and that will help me to get the vertical component of the velocity at the point where I'm studying it. Considering the horizontal component of motion, initial velocity ux will be equal to u cos theta, acceleration will be a negative g, and if I let t1 be the time to reach the maximum height, meaning if I use the first equation of motion, at maximum height v is equal to 0 and acceleration is negative g. When I substitute in back, I get the time taken for the particle to reach the maximum height as u cos theta over g. Now we realize that as the particle is launched from the original position, as it's attaining the maximum height, the remaining distance, the remaining parabolic path to be covered is ultimately the same as what has been covered, meaning at the maximum height is halfway the distance or the path, the parabolic path from the point of projection, and if you sum up the two, it ultimately gives you the total time for the particle to hit the ground from the point of projection. So we realize that the time to reach the maximum height is equal to time taken by the particle to hit the ground from the maximum height. Let's look at the time of flight as the total time taken by the particle to hit the ground from the point of projection. So if t is representing that, then I can find it from the equation s equal to ut plus half at squared, whereby my acceleration will be a negative, still u will be the horizontal component and s will be the distance, vertical distance. But now since the particle is getting to rest, meaning vertically it is not covering any distance, so it will be a 0. So when I substitute in back, I have the initial component of horizontal component of velocity u cos theta. I have the t as capital T. Substituting back, I make t the subject. That will be the time of flight, the total time, which is ultimately connected to the time taken for the particle to reach the maximum height, and that will be twice t1. So time of flight is equal twice the time taken for the particle to reach the maximum height. Equation of the parabolic path, or the equation of the path taken by the projectile. Now this one we are going to use still equation s is equal to ut plus half at squared, and we need to look at the perimeters. One, at the point where we are studying the projectile path, we realize that the vertical displacement is y, which is representing distance. At that very point, the vertical component of velocity, will be u sine theta, because it is the initial velocity with which this particle is being launched vertically. So u sine theta. And now the time at that point where we are studying the projectile, at that very point we are going to use the horizontal distance from the point of projection to where it is being studied, and the horizontal speed from the point of projection to where it is being studied, and that will be x over u cos theta. So when I substitute in back, I get my equation of the projectile, or parabolic path as y is equal to x tan theta plus gx squared over 2u squared into 1 plus 10 squared theta. So that equation is very, very important. That's why I highlighted it in a red color, because it's very important as far as projectile motion is concerned. We use it to find to solve very many problems, finding the angle of projection, finding the distance, finding A, B, C, D, initial velocity, etc, etc, etc. So far we have how many? 5 equations. So far 5 equations. They are very important for this particular case. Lastly, I want to look at the final velocity with which a particle can clear the wall, if that is the wall. The velocity with which the particle, if that's the ball, will clear the fence. So meaning that's the final velocity at that point, which is v in the red color in the diagram, v in the red color. So I'm going to play with vx and vy at that point, making an angle alpha. So what I will do, Pythagoras theorem will help me very fast. Vx squared, which is the velocity, horizontal velocity of the projectile. And we agreed from the start that this velocity is the same throughout, it remains unchanged. So that will be u cos theta. But again, the vy, as the particle is describing this parabolic path, at every point, the vertical component of velocity keeps on changing. So we shall find that vertical component of velocity at that very point. Meaning, one, you need to know the vertical distance from the horizontal line to where that particle is being studied. 2, you need also to know the time at that very particular point. Meaning, if I know the horizontal distance from the point of projection to where the particle is being studied, and also I know the horizontal component of the initial velocity, then I can get what? Vy from the equation. Actually, it is our second equation from this very tutorial. So if I have the two velocities, then I can get the resultant velocity, that is the velocity with which the ball will clear the fence. And then I can also get the angle at which it is actually doing that, using the tan inverse of vy over vx, whereby vx is the same as ux, which is u cos theta. So these are how many equations? They are basically 6 equations. They are very, very important for us to maneuver cases similar to this very case, where a particle is projected from the horizontal ground at an angle, given or not given, and it's given or not given initial velocity, making a maximum height, gets to the ground, and you are required to find anything missing here. So you first need to study the motion of the particle, understand it deeply. This is for you. Go through this item. I worked it out already, though the responses, final responses, are in the bracket. You can use 9.81, that is for math. Physics can use 9.8, and then expected responses are there. For more activities, just tap on that number and get this book. You will thank me later.